Welcome back to Data Dive, where we explore the intriguing world of data structures and their impact on our digital lives. I'm your host, Your Name, and today we're going to delve into indexing structures, those unsung heroes that help us quickly locate the information we need. Whether you're a seasoned developer, a data enthusiast, or just curious about how databases operate, this episode has something for you. Let's jump right in. Imagine stepping into a vast library, searching for a specific book. Without an index or catalog, you'd find yourself wandering the aisles for hours. In the realm of databases, indexing plays a similar role. It keeps additional metadata close at hand, like a signpost to help you swiftly locate your data. However, there's a trade-off to consider. While indexes can speed up queries, they may slow down write operations. This means databases don't automatically index everything. Instead, it falls to you, the developer, to determine which indexes to create based on your application's expected usage. This approach helps you maximize performance while keeping overhead low. Let's dive into our first type of indexing, key-value data indexing. This foundational structure is the building block for many more complex indexes. At its core, a key-value store is often implemented as a hash map. Think of it as a way to quickly find a value's location based on its key. For example, if you have a data storage system that appends data to a file, you could maintain an in-memory hash map where each key points to the byte offset of its corresponding value in that file. When you add a new key-value pair, you simply update the hash map to reflect the new offset. When it's time to look up a value, you consult the hash map, jump to the right spot in the file, and retrieve your data. This method is not only straightforward, but also efficient, similar to how Bitcask, the default storage engine in Riak, operates, allowing for high-performance reads and writes as long as all keys fit in memory. Now let's consider a common scenario. What happens when you have a lot of writes but not many distinct keys? Picture a popular cat video where the key is the URL and the value is the play count. Each time someone hits play, that count increments. You have numerous writes, but a manageable number of keys, making it feasible to keep all keys in memory. The challenge here is preventing disk space from running out as data accumulates. One effective strategy is to break the log into segments. When a segment reaches a certain size, you close it off and start writing to a new segment. This is where compaction comes into play. Compaction involves removing duplicate keys from the log and retaining only the most recent value for each key. By merging segments during this process, you can keep your data storage efficient and manageable. So, how does this merging process work? Each segment has its own in-memory hash table that maps keys to file offsets. When you need to find a value, you first check the most recent segment's hash map. If the key isn't there, you move to the next segment, and so on. This keeps lookups efficient since the number of segments is minimized through merging. Implementing this in practice can be challenging. For instance, the CSV format isn't ideal for logs. A binary format that encodes the length of strings can be more efficient. Another important consideration is handling deletions. When you delete a key, you add a tombstone record to the data file, signaling the merging process to discard any previous values for that key. A crucial point to remember is that if the database restarts, the in-memory hash maps are lost. To speed up recovery, you can store a snapshot of each segment's hash map on disk, allowing for quicker loading back into memory. Now, let's switch gears and discuss the benefits of an append-only log structure. At first glance, it might seem wasteful to append data rather than overwrite it, but this design offers several advantages. First, sequential writes are generally faster than random writes, especially on traditional spinning disks, and even solid-state drives benefit from this approach. Additionally, this design simplifies concurrency and recovery. If a crash occurs while writing, you won't end up with a corrupted file containing a mix of old and new values. Plus, merging old segments helps prevent data files from becoming fragmented over time. Next up is another data structure, the sorted string table or SS table. Each segment in this format is sorted by key. While this might seem to complicate sequential writes, it actually provides significant benefits. Merging segments becomes straightforward because you can use a method similar to merge sort. You read from multiple input files side by side, copying the lowest key to the output file until all segments are processed, resulting in a new sorted merged segment. The beauty of SS tables is that you no longer need to keep an index of all keys in memory. Instead, you can leverage the sorted order to find keys efficiently. For instance, if you're looking for a key like handiwork, you can quickly determine its position based on its relation to other keys in the segment. But how do you ensure your incoming writes are sorted in the first place? Maintaining a sorted structure on disk can be complex, but it's much easier to manage in memory. You can use well-known tree data structures like red-black trees or AVL trees to insert keys in any order and read them back in sorted order. And that wraps up our exploration of indexing structures, from key-value data indexing to the intricacies of SS tables. Understanding these concepts is essential for optimizing database performance and ensuring efficient data retrieval. Thanks for tuning in to this episode of Data Dive. If you enjoyed the show, don't forget to subscribe and leave us a review. Join us next time as we continue to explore the fascinating world of data structures. Until then, keep diving deep into data.